So y is the derivative is this f of x, and that's the last bit. Capital F of x is defined like this: to c to x f of t dt. That's the function discussed in Fundamental Theorem of Calculus Part 1. Now we're differentiating, and there's no other tool. This is very, very fundamental result. Whenever you're dealing with a derivative result, and that is so fundamental, do you know what we did? We took this LIM, h approaching 0, the f of x plus h and minus f of x. This is so fundamental result, so you have to go back to the very beginning and you have to deal with it. All right? So this one is actually equal to f of x plus h minus f of x, right? That's the same thing. Let me give you an interpretation of this picture. Here is a c, and here is x. Maybe here is x plus h, correct? And the function look like that, and that's a graph of y equals ft, right? F of x, capital F of x plus h measures the area up to here, correct? That's what capital F of x plus h measures. How about capital F of x? That measures up to here, right? You see they're canceled out, leaving only between x to x plus h, f of t dt. Fair enough? This one, capital F of x plus h, which is area from c to x plus h, according to that definition. Capital F of x is area from c to x. Here's a c to x. If they subtract, they cancel, you're leaving just that part. And h is going to be very small, right? It's almost the same. So they use this type of technique. In between and here, there must be x star so that it's a maximum in between that interval there. We don't know where it is, but you know there is, right? Maximum. It's called extreme value theorem. If you have a closed interval, continuous function, there must be a maximum value there. So it is obtained by that. And this, there must be x tilde that hits the minimum in between there, right? And this x star is in between x plus h and x. And this x tilde, we only know the existence, is also in between these two. Right? So as h approaches 0, that's our scenario. What's going to happen to x star and x tilde? Where are they going? Because x is fixed, only thing here is changing is h. C is not changing, x is not changing, only h is changing. So if it is like this, x star is trapped in between x and x plus h. X tilde is trapped in between x and x plus h. As h approaches 0, what's going to happen to these two values? Where does that go? X, right? What is this theorem called? By squeeze theorem. All right? By squeeze theorem, they must go, don't know what that is, but it must go to x. So, because it's the highest point, this area here, this is the area from x to x plus h, right? F of t. I'm going to write down something in here. H times f of x star. Can somebody tell me what this one measures? In terms of area. This is area underneath the curve over the tiny interval, right? How about this guy? H times f of x star. H is this length here, right? F of x star is the tallest height here, right? So that's going to be the rectangle. The highest rectangle, everything is underneath it, right? Therefore, this must be bigger than this one here, right? This is the highest one that covers the top. How about the lowest one? H times f of x tilde, right? That means the lowest bottom in here. So the picture looks like exaggerating some crazy thing is happening here. That's h times f of x star. That's h times f of x tilde. Area underneath it here. area underneath the whole thing. That must be trapped in between. Good? Now you divide both sides by h. Now we enter the derivative of that. This was a derivative of capital. This is the slope of a secant line of capital F of x, right? So that's trapped in between f of x star, f of x tilde, right? Now what happened to h? H is approaching 0. As h approaches 0, what happened to this one? X star approaches x, right? Remember the squeeze theorem? X star approaches x. So if inside approaches x, what's going to happen to the whole function? If x star approaches x, f of x star is going to approach f of x. But under what condition of f that guarantees this happen? Because f of x is what kind of function? What? Continuous is correct. Continuity. Because the function is continuous, input value is exactly telling you what happened to the output value. What about this one? Yeah, x tilde is also going to f of x. Now this upper bound and lower bound, they're heading to the same direction, right? What could happen to that guy? Go to the same place, right? By what theorem? Squeeze theorem. So that was the slope of a secant line. That approaches that. So this proves the derivative at x is little f of x. Right? That was it. That's the whole thing.